Today we're going to talk about Lecture 8, and specifically we're going to talk about electrochemistry, corrosion. How do you set up a kind of electrochemical cell to deal with galvanic corrosion or electrochemical kind of corrosion using basically how do you define a cathode, how do you define an anode, where are electrons flowing, what material is going to corrode, what material is going to electroplate, how do you deal with the Nernst equation when you're out of ideal or standard conditions, and then how do you basically protect a material from corroding using a sacrificial anode. So it sounds like a lot, but actually corrosion's pretty straightforward, and again, it's a very kind of lucrative field. So there are a lot of job openings basically for if you become an expert in electrochemical reactions or corrosion. And the reason why there's a lot of job openings is because corrosion is an extremely problematic issue. So we will typically spend in the U.S. about 5% of our GDP per year to prevent corrosion, or to kind of perform maintenance, or to deal with kind of failures due to corrosion. So really stable career choice for you. A lot of the experts have kind of basically moved on, or basically got different jobs, or there's kind of not a lot of experts left. So the field is kind of lacking. Material science used to be a lot, almost entirely kind of metallurgy, and metallurgy had to deal, obviously materials that are metallic are going to corrode more than your polymeric materials. So with the rise in material science of kind of biomaterials, composites, polymeric materials, a lot of people have been drawn to that side of material science. So electrochemistry has kind of been left not in the dust, but there's kind of a lack of kind of personnel there, essentially, or experts. So really kind of really stable career choice, and also you could also make quite a bit of money too as that. But anyways, let's get so there are different types and lots of different types of corrosion. So uniform attack, galvanic, crevice corrosion, pitting and granular corrosion, also stress corrosion cracking, so SCC, stress corrosion cracking. Crevice corrosion, you could run this, I think it was a G48 ASTM test to kind of measure the amount of crevice corrosion, or that might be in my days back basically in Pittsburgh working in the metallurgy industry. This SCC, or stress corrosion cracking, and actually we'll see that on the next page here. This is an extremely really dangerous and problematic form of corrosion. So you could kind of imagine when you're, this is really problematic when you're drilling basically pipelines. So or you just have a pipe there's lots of kind of flowing, kind of really kind of nasty kind of materials. So if you're in an environment that has like a lot of, sulfuric acid, you could basically have this idea where at temperatures and at high temperatures and kind of these really kind of corrosive environments, even just a static load on a material, the combination of temperature, environment, and load will cause your material to kind of catastrophically fracture. And kind of when this will occur, and predicting this is a really critical and difficult problem to do. There's a lot of kind of different testing methods to try to estimate, a given material, how long it will survive in a particular application. And obviously, it's this is a critical problem in the kind of oil and gas industry. So if you could kind of study this and figure out a first principle method of like when this will occur, you'll make yourself a lot of money and patent a lot of things. But anyways, the whole point here is there's lots of different types of corrosion. We could spend a whole class on the different corrosive mechanisms, but we are going to focus primarily on kind of electrochemical corrosion. So electrochemical corrosion is governed by basically these redox reactions. And the whole idea behind corrosion here is where are electrons lost and where are electrons gained. That is going to tell us what material is going to corrode, what material is not. So that's the name of the game here. And so hopefully you remember from chemistry, redox reaction. So in that term, redox is kind of composed of two parts. So rid is reduction, and then ox is oxidation. So two reactions. In this electrochemical reaction, two things are happening: reduction and oxidation, here and here. So hopefully you remember where electrons are gained. So reduction, we gain electrons. Oxidation, we lose electrons. So let's scroll down a little bit here. And again, it's just kind of restating just what we've kind of said here. So oxidation, the element's going to lose the valence electrons. Reduction, the material gains the electrons. So a couple of examples of oxidation, reduction. So again, see here, we start off with the material. We become this kind of positive cation. And then now you basically add, or you're losing kind of the electrons. So the electrons are, we lose 2 electrons here, we lose 3 electrons there. So this is an oxidation reaction. Reduction, we start off as kind of this positive, this cation, and we're gaining the material that we form here. We've gained electrons in this reaction. So reduction, remember, reduction, we gain electrons. Oxidation, we lose electrons. So we're going to kind of talk about this redox reaction and what material is going to, again, in our kind of electrochemical cell, we're going to have a cathode, and we are going to have an anode, and we're going to see what reaction, reduction or oxidation, occurs at each of these kind of materials. So we'll get to that in just a second. So that's kind of the basics. Basically, when we're dealing with electrochemical corrosion, and galvanic corrosion is kind of another term for it, it's all about these redox reactions. So one of the ways that we kind of could measure or kind of see, because corrosion basically comes into play when you have 2 dissimilar materials. They could be metals, they could be polymers, whatever, and if you have 2 dissimilar materials, let's focus on metals for this instance. 2 dissimilar materials, you put them together. If there's kind of some conducting like fluid or material between them that is able to conduct electrons, due to the electronegativity difference, you're going to have basically one material grabbing electrons and pulling electrons away from the other material, and one material that's giving up and losing electrons. And as you lose electrons, you lose material, you corrode. If you're gaining electrons and grabbing material, you're not corroding. So the one way we could test, and again, this is important, right? So if you have like a pipeline, so usually you have some pipe, let's say made of some material, let's say it's like stainless steel, but you might have some like bracket on here, or something, my poor drawing skills. This bracket might be made of, maybe pure iron, who knows, maybe copper, just throwing an example there. You'll have corrosion there. So if those 2 dissimilar metals are in contact, there's going to be corrosion. So we need to kind of figure out what material is going to corrode, how fast it's going to corrode, and when will catastrophic failure occur. So one way we could test that is by basically setting up this kind of experiment where we have this kind of electrochemical cell. And we want to talk about basically these half-cell reactions. So the way that we set it up, and we'll look at a diagram in a second, we define one material as our cathode. Typically, you'll have this as the positive terminal. We'll see why in a second. And generally, if you define your cathode as positive, and if you set up your cell correctly, the electrons are going to flow into your material right here. The anode, typically defined as your negative terminal, it will give up electrons. So if I have, and we'll see a better example of this in a second. So if I have my material here, I'm going to say this is my negative terminal. This is going to be my positive material. Material. I'm going to kind of attach a wire here. I'm going to measure the voltage from this. So this is negative, so this is my anode. We just said that this is where basically the electrons are going to flow from your anode, from your anode to the positive terminal, which is your cathode. So here we're losing electrons. So we're lose E. What reaction is going down there? Oxidation. Lose electrons. What's happening at the cathode? We are gaining electrons. That is reduction. If I'm losing electrons, what material is going to corrode? The anode should corrode, and the cathode should not. Now, before we even we've just identified that the anode is where we're going to lose electrons, where we're going to have oxidation. That is going to be, if we lose electrons, we oxidize, that material is going to corrode. At the cathode, our positive terminal, we are going to basically gain electrons. We are undergoing a reduction reaction, and that material will not corrode. Additionally, if electrons are flowing this way, the voltage that we should measure should be positive. So, and this also kind of, whether an electron is going to lose electrons or gain electrons, one of the key material properties that we're going to look at is this value, again, going all the way back to lecture 1, these values, how we determine whether a material is going through covalent bonding or ionic bonding. We are going to look at En, which is electronegativity. And that will give us some idea, and we could kind of guess at what material is going to grab electrons, what material is going to lose electrons. So we have a little nice, a much nicer kind of schematic in our notes. So as you can see here, again, same idea. So our anode right here is our anode right here is your where we have our oxidation occurring. So we are losing electrons. As you can see, electrons are being pulled from the anode to the cathode. So we should expect, again, if this is set up correctly, our voltage that we should measure is positive. If they float in the opposite direction, the voltage that we measured should be negative. At the cathode, we're going reduction, so we gain electrons, just as you can see. So gaining, here oxidation, we lose electrons. Burn this into your memory because this is the exact kind of idea. So here we're going to lose material, so this material is going to kind of shrink, and here we're going to gain some material as well. And again, they're connected through this wire. There's this electrolyte. There's some medium going on there. So that is where that is basically how these electrons are being basically transmitted. So let's actually look and work with an example of how we can figure out what material is going to corrode, what material is going to not corrode, and what is kind of the potential difference between these two materials. So let's go ahead and get started. So we will look over here. So the example, we are at a very special set of conditions here. I'm going to change my, so we're going to do this experiment for this electrochemical cell at STP conditions. So these are standard temp and pressure conditions. So if we're at these conditions, we know that our pressure is approximately 1 atm, so room, basically standard pressures. Our temperature is basically at room temperature, so 298 K. And you see here that our iron is immersed in the solution, a 1 molar solution of Fe2 plus ions, and our copper is immersed in the solution of 1 molar of Cu2 plus ions here. So that's kind of the key. If you meet all these conditions, if temperature is this, pressure is this, you are at these standard temperature and pressure conditions. Now this, what I want to do is connect these two with, basically I want to connect these two with a wire. I want to measure the voltage and see where our electron's flowing. So that's kind of the whole goal of this part of the course, and to kind of, when you set up an electrochemical cell. So we want to see what material is going to grab electrons, what material is going to lose electrons, what material is going to corrode, what material is not going to corrode. And we want to get a value for that voltage measurement. So if we're at these standard temperatures and pressures, one of the first things is, like, how do we set up what is materials the cathode, what materials the anode? So again, we could kind of make a guess before we even start and kind of looking at that kind of table, what material is going to lose electrons, what material is going to gain electrons. So what is, and you can kind of look this up online, what is our electronegativity value in for copper? So electronegativity, let's do materials, let's do a little table, material. So copper, and our other material here is iron. So which one, what is the electronegativity of copper? So copper has electronegativity of 1.9. Iron has electronegativity of 1.83. Higher electronegativity, it means it wants to grab more electrons. Lower electronegativity, it wants to give up electrons. So already I'm going to say, okay, copper, I'm going to set this up as my positive electrode because, again, my cathode, because cathode, what is going to happen at the cathode? Cathode, we are going to have reduction. We are going to gain reduction. We are going to gain electrons. Here at our anode, so I'm going to say this is my cathode. You see that by the positive sign. Here, this is my anode. What's going to happen here? We are going to have oxidation, ox, and I'm going to lose electrons. That's my guess just by looking at those electronegativity values. So we will actually kind of prove this quantitatively, but that's where you kind of can first start off with in setting up this system. So we think that the electrons are going to go from here, here, electrons. And if this is the case, and we've set up our cell like this, we should measure a positive voltage. So let's go ahead and confirm this. And what we're going to actually start off doing is writing basically a half cell reaction and a full cell reaction. So we know that at my cathode, so let's go over here. I'm going to write my half cell for the cathode. So what is happening to this material? So we need to incorporate our electrons into this material. So we're going to write basically the half cell reaction for the cathode. So in order to incorporate the electrons, what's going to happen is I have, and let me look at my colors real quick, see if I can match. This looks close enough. So I have floating in here these Cu2 plus ions all over the place. So 2 plus, Cu2 plus, again, all those ions floating over there. So what's going to happen is this Cu2 plus ion is going to combine with electrons, and we're going to form more copper on our material here. So we're going to electroplate, we're going to essentially grow our material in that cathode. So let's write out the reactions. So in the solution, the Cu2 plus is going to combine with the 2E minus, again, charge neutrality, and we're going to form. So that's it. What reaction is this? We are gaining electrons. Again, this is reduction. So let's look at what's happening on the opposite side here. And I'm going to change my thickness just a little bit. I'm getting a little bit fancier here. So here on the other side for our anode, our half cell reaction. So what's happening here? We are losing material, right? So we're going from Fe to Fe2 plus 2E minus, right? This is the reaction that's occurring here. So what's happening to our material? Well, we're losing material, right? So we are going from Fe to Fe2 plus minus. So this is, or we're losing electrons. This is oxidation. And what happens is you essentially this material shrinks a little bit. So we are corroding here. So corrosion is happening over here. We are gaining material on the anode corrodes, and it's giving away material to the cathode. That's it. So that's our half cell reactions for both sides. So now let me erase here real quick. Remember that we are at standard temperatures and pressures and all of that other good stuff. So now we will see, we could write our full cell reaction. So the full cell reaction is going to be the following. You just add those, so it's Fe goes to Fe2 plus 2E minus, plus you add Cu2 plus 2E minus goes to Cu. So what happens here? The 2E minuses cancel out when you add essentially these two equations. So you're left with Fe plus Cu2 plus goes to, excuse me, erase that right there, goes to Fe2 plus Cu. That is your full cell reaction for this electrochemical cell. That's it. You're done. You've got it. That's basically it right there in a nutshell. So we haven't answered this question of what is the voltage, right? So let's go back to our notes, and we can basically figure out for each of these half cell reactions, we're going to have an E naught of our cathode. Basically, for this reaction, there's going to be some basically electromotive force or some voltage associated with this reaction. So E naught of our cathode, and we're going to have an E naught. Let me switch pins. E naught of my anode. And for the full cell reaction, I'm going to erase again here. We know the electronegativities. We are going to figure out the voltage is just going to be the E naught of our cell is just going to be the E naught of the cathode minus E naught of the anode. So that is going to be our equation. So let's figure this out. What is E naught of our cathode? So let's go back to the notes. Excuse me for, you're going to see some switching around here. So let's look at what is our standard potential for this reaction. So what material are we working with? So let's look at, we are looking at copper here. So what is the reaction for copper, the reduction? It's this point, and I just, here, let me erase that a little bit or draw it a little bit finer. So here's the copper. That is just going to be 0.34. So that is the reaction that's happening in my, I'm reducing here. So that is 0.34 minus, what is the reaction happening at the anode? What's our material we're working with? Iron. So iron's right here. So what's happening there? That is the potential for reduction. So again, our material is not doing, this is, again, you subtract by this reaction value, this value here. So the E naught of our anode is that. So it's minus, excuse me, that is that is a different lecture, minus 0.44 volts. So minus a negative 444. That is going to equal to what? Add that together. I don't even need Mathematica for this. 780 volts. So clean that up just a little bit right here. 780 volts. That's it. That's the E naught of this cell. So again, it's positive. We've set up our cell in the correct order. If we would have flipped this, you would see the value be negative. And again, so the electrons is actually flowing in the opposite direction. So that is how you kind of solve your first electrochemical cell. So let's go ahead and do another now. Example, and see what material is going to corrode, what material is not going to corrode in this electrochemical cell. So right now we are working with a couple materials. So iron, we're working with zinc. What is the electronegativity? Well, we know from last time that for iron it's 1.83. For zinc, it is, if you look up in the periodic table, 1.65. And now let's go ahead and proceed. Where do we think the electrons are going to flow? Well, they're going to be, reduction is going to happen here. We know that oxidation is probably going to happen here. So I'm going to write here, I'm going to guess that this is my cathode here. This is my anode material, switching here. And we are going to connect, measure the voltage. We think that here we are going to have reduction. So we are going to gain electrons. So my half cell reaction is what? Well, it is just going to be Fe is going to gain. So Fe plus 2E minus. And we're going to go to Fe. Our zinc, on the other hand, is going to go our anode material. So this is, we're going to have oxidation. We are going to lose electrons. And then we are going to go from Zn to Zn2 plus 2E minus. We're giving away electrons. So that's our half cell reactions. So now our full cell reactions. Let me switch here. So let's go. My full cell reaction is just going to be adding those two together. So it's going to be, excuse me, Fe2 plus the 2E minuses are going to cancel, plus zinc goes to Fe plus zinc. That's it. So what about my E naught of my full cell? So we are, in this instance, we are at standard temperature and pressure. So what does that mean? Pressure equals 1 atm. Temperature equals 298 K. And look at it, we are in 1 molar solution of our own ions. So we know that E naught of the cell is going to equal to E naught. Ooh, actually, let me redo that. I know that my E naught of the cell is going to be the E naught of the cathode minus the E naught of my anode. So let's go back. We know what is going to be our half cell reaction for our cathode material. So our cathode material is iron. So let's go ahead and look that back up. So we are dealing with, we could use this table only when we're at standard temperature and pressure conditions. So our cathode material is iron, right here. Our anode material is zinc. So we're going to do minus 0.440 minus minus, so basically a plus 0.73. So let's go ahead back there. So it is going to be minus 0.440 minus minus, so plus 0. Let's look at that value one more time really quickly. It's plus 763. and that is going to give us a value of 0.323 volts. So again, we've set up our cell correctly. If we would have flipped, you would read a negative value. So now you're basically set up your cell incorrectly. The anode material that you thought was not your actual anode material. So if we read a positive voltage, we have set up our material correctly. Electrons are flowing basically this way. We are grabbing them over here. So electrons are flowing into here. This material is expanding. This material is contracting. So zinc is corroding. We're losing material. Iron is not. So that's basically how you solve almost every corrosion problem that you'll really run into. Oh, excuse me here. My OneNote crashed. We'll come back with this in just a second. There we go. So let's look. So what happens when we aren't basically at these standard temperature STP conditions, so standard temperature and pressure condition? Well, we have a really great equation that we could work with. Let me scroll down. We are going to use the Nernst equation. So the Nernst equation is when we are not at STP conditions. So when either temperature is not 298 K, and pressure is not 1 atm, or we're not at these kind of room temperature and 1 molar solutions. So how do we figure out, what is, the whole point of this is once you're not at STP, we can't use this equation. This E naught of cell equals E naught of cathode minus E naught of anode. So how are we going to figure out what is our potential of any kind of any type of electrochemical cell? Here's an anode, cathode, connected here. How can I measure what's the voltage, or how can I kind of get to this expression? Well, you can derive it basically from thermodynamics. So it changes the change of potential as a function of temperature and activity or concentration. So you'll see this term electrochemical work. So work is defined as this, where F is your Faraday's constant. So F will be equal to 96485 coulombs. E, that is going to be your cell voltage, as you see here, and N is just the number of moles of electrons. So for all these problems, whenever we had the kind of this 2E minus, N would be equal to 2 here. So so far, when we've been calculating E, the E that we've been calculating here is for this equation here, whereas just your potential E naught right here. So now, how do you get to kind of the more general expression? Well, we need to kind of figure out, well, how will our free energy change as a function of temperature and pressure? So all we do is we'll take this expression here. So our change in free energy is going to be your kind of this initial standard temperature and pressure gives, which is just plugged in up here, over the sum basically of all the activity of the products over the reactants. So the arithmetic product and reactants. So let's go to the next page. See here, we just plugged in basically from that previous expression for our basically E sub naught, or your standard temperature and pressure conditions. But this is the equation that we want to look at and deal with. So you can see we're going to make one approximation here that the activity, and actually we're going to ignore, this is going to be products versus reactants. So we're going to say that the activity is approximately equal to your concentration. So let's look at the last half cell reaction that we did, which was Fe2 plus zinc goes to zinc 2 plus Fe. So that was our full cell reaction here. So if we follow through this equation, our Nernst equation is going to be E minus E naught equals minus RT, gas constant, over NF, natural log of the concentration of our products, so Zn2 plus. We are only interested in the ions here. The activity here of Fe, or kind of these non-ion materials, those are just going to be 1, so we don't have to deal with them. But we want to deal with these guys, these ions here. So products, concentration of zinc 2 plus ions over concentration of Fe plus ions. Now, what happens when we're at STP? Well, we know that the concentration of Zn2 plus is equal to 1 molar. We know that the concentration of Fe2 plus is equal to 1 molar. So what happens? What is the natural log of 1? Ln of 1? That's just 0. So this expression disappears, and you're left with E is equal to E naught of your cell, which is just what we have at standard temperature and pressure conditions. But what happens when that concentration is not 1 molar, when we're not at standard temperature and pressure conditions? Well, then we have to use the Nernst equation to figure out what is going to be our E of our cell. So basically, when you have a setup like this, minus, positive, connect them, what is going to be the voltage coming out of that condition? Now, there's a cool kind of idea you could have here. You could actually, at certain conditions of temperature and concentrations, you can flip what material corrodes or what material does not. So initially, when E is equal to 0, you can solve basically for when is this material going to flip? I.e., when can we tune temperature or can we tune our concentrations so that actually we could flip and make our cathode material corrode and make our anode material not corrode. We can basically flip what's the anode and the cathode basically just by tuning temperature or by tuning our concentrations. So that's what we're kind of working with here in the Nernst equation. So you'll do a couple problems like that in the problem set. Now there are a couple I think continuing this discussion of like how can we change or shift what's going on? How can we change or shift what material is going to corrode, or how do we protect against a certain? Let's say we want a material to not corrode in a particular instance. There are definitely methods to prevent. There are definitely methods to prevent or protect against this galvanic corrosion. One of the most cool methods, again, you could kind of there's lots of ways you could kind of do this. So you could do an insulating layer or a coating layer to break up the metallic contact. So polymers are really nice for this, but there can still be basically some idea of like crevice corrosion in pockets. But let's say you just want to still work with metals. One way you could do it is with this idea of a sacrificial anode, or sacrificial anode here, or cathodic protection right here. So let's talk about a sacrificial anode first, because the other one basically uses this imposed current. We'll talk about that in just a second. So let's look at an example right now of some basically a sacrificial anode. So what is going to happen here? So I know that zinc has an electronegativity. So again, let's make a table. Material, zinc 1.65. I know also that iron, remember, is 1.83. And copper. What is the electronegativity of copper? So let's look, we can kind of look this up in our, again, periodic table and see what is our value. So for copper, we have our electronegativity is 1.9. So if we connect all these in a circuit, copper, where are the electrons going to flow when we have copper? Well, copper is going to grab electrons from here, from iron, right? Because its electronegativity is greater than iron. And it's also going to take electrons from here. What is going to happen for iron? Well, iron is going to give electrons from here, and it's also going to take electrons from our zinc as well. So, and what happens to zinc? It gives to both. Now, sacrificial anode. If we just hooked up, let me erase here in a second. If we just hooked up, and if we ignored this section here, we know, and we've you could show it previously, that iron is going to corrode because the electronegativity of iron is less than, this is going to be our cathode material, this is going to be our anode material. Now, once we hook this up, again, the material wants to pull electrons from the easiest source. So what is the electronegativity difference between iron and copper? It's just 0.7 change in electronegativity, right? What about the difference between copper and zinc? Much greater, right? Electronegativity difference, it's going to be 0.25 or 0.07, excuse me, 0.07. So we're going to pull a lot more electrons from zinc than we will from iron in this system. So by doing so, by hooking it up in this way, this material is going to corrode much more, and iron is, there will still be some electrons pulled from iron to copper, but we're also pulling electrons from zinc into iron. So we're supplying electrons electrons are flowing in from here, we are still losing some electrons to copper, but again, copper wants to pull more electrons from zinc. So this material is our sacrificial anodes. We're going to sacrifice We're going to sacrifice this material in order to protect. We're going to protect iron from corrosion. So this material is going to corrode. Iron will not, or at least will minimize the corrosion there. So that's one idea of the sacrificial anode. Another type of protection is this kind of imposed current or cathodic protection. So you can basically hook up a power supply and bias your current. So if I don't want iron to corrode, again, I can just apply some basically a power source and impose a current to make sure that electrons are not being taken away from iron to copper. So I can impose a current to basically drive electrons into the material that I want to protect. So that's another kind of more expensive way to do it. So you'll have to kind of play around with that. And decide basically, is your material or is your application, does it justify essentially that cost of having to kind of continuously supply this power source? But yeah, that's about it. That is the basics of electrochemical corrosion. You can read a little bit more. There's some basically Kroger-Vink notation that's associated with corrosion and oxidation and reduction and kind of these flows of electrons. We're not going to talk about too much of that in class, but you can definitely read up on it in the OER. And if you have any questions, you basically produce these kind of really cool Brouwer diagrams, so you see what reaction is dominating at different concentrations of partial pressures. It's a really kind of unique and cool derivation, so I'd encourage you to do it. But yeah, that's about it. Have a great day. Bye.